Good morning and welcome to the final 2024 edition of Great Designs in Steel Technical Webinars. My name is Brian Esterberg, and I'm the Senior Market Strategist at the American Iron and Steel Institute. Today, we're pleased to welcome our guest speaker, Dr. Mohammad Shojaee, Postdoctoral Fellow at the University of Waterloo. His presentation, A Novel Approach for Precise Calibration of Force-Based RSW Failure Criteria Implemented in LS-DYNA. Mohammad will take us into a much deeper dive of this work at the University of Waterloo than was formally presented at GDIS last spring. So let's get to it. Your microphones have been muted. Please use the Q&A feature today in Zoom to submit your questions. We will not be utilizing the chat or raised hand feature. Again, submit through the Q&A feature. And my colleague Hisham Aizat, our Senior Technical Advisor, will join Mohammad to address those questions following the presentation. The presentation slides and a recording will also be made available on demand following today's webinar. It is now my pleasure to turn it over to and welcome Dr. Mohammad Shojaee.
Thank you, Brian. Okay. Hello and good morning, everyone. My name is Mohammad, and my presentation today is going to be titled A Novel Approach for Precise Calibration of Force-Based RSW Failure Criteria that are Implemented in LS-DYNA. Here is an outline of my presentation. I'm going to start off with an introduction to third generation advanced high strength steels. I'll introduce the resistance spot welding process itself. I'll introduce the failure prediction criteria that are used for spot welds, the component test, and the motivation of my research. Then we'll get into the result and discussion tasks. In task 1, I'll deal with process optimization. Task 2 and 3 deal with different types of loading modes in spot welds. Task 2 deals with combined shear tensile loading of spot welds that is performed via KS2 test here. And I'll assess the validity of some of the failure loci that are suggested in the literature for this type of loading. In task 3, I'll deal with another loading type, which is tensile bending loading of spot welds that's characterized by coach peel tests. And lastly, I'll mention in task 4 the results regarding the weld group or the component tests. So starting off with the introduction, we know that within the automotive industry, there are a few goals that are commonly pursued. These goals include improving the fuel efficiency of the vehicle and at the same time enhancing the safety of the passengers simultaneously. Now, following these two goals at the same time has resulted in a further and further adoption of steels that are referred to as advanced high-strength steels. If you look at the pie charts in the middle of the screen here, we can see that between 2010 and 2040, so in around 30 years, it is estimated that the usage of steels with relatively low strength, such as mild steels or high strength low alloy steels, is going to diminish. And at the same time, we're going to get much more adoption of steels such as advanced high strength steel or ultra high strength steels. Now, the main reason for this trend is the properties in terms of strength and ductility that the advanced high-strength steels are able to provide us. So the first generation of these steels, they were much leaner than the third generation of advanced high-strength steels, and they had good formability, but they were not able to attain high strengths. The second generation of advanced high-strength steels have good formability and good strength, but they come in at an expensive price point. So the third generation of advanced high-strength steels are the ones that really bridge the gap that existed between, in terms of the properties between the first generation and the second generation. And that's one of the reasons that they're really critical for the automotive industry. Now, one of the main reasons that we are able to get the properties of third generation advanced high strength steel in terms of strength and ductility is related to transformation induced plasticity, or the TREP effect, where we get localized transformation of retained austenite within the microstructure of these steels to martensite at the onset of necking, which inhibits the necking to higher elongations, basically. Now, as good as the properties of the third generation of advanced high-strength steels get, they still have to be joined together. And by far, the most common joining technique in the automotive industry for steels is resistance spot welding. This is a relatively straightforward joining technique where two copper electrodes clamp the two sheets that we want to join together from the two sides. And upon establishing a predetermined amount of force and welding current, we get localized heating at the interface between the two sheets where we have the highest resistivity. And upon melting and cooling, we get a solidified joint in between the two sheets. Now, obviously, because of the sheer number of spot welds that exist in a typical body-in-white structure, as shown in the top here, it is very important for the automotive industry to be able to predict the failure of these steels, because that is what ultimately determines the crash worthiness or crash performance of the whole structures. Now, whenever we're talking about prediction of failure in resistant spot welds, there are two techniques that are commonly applied. The first technique is referred to as mesoscopic models or mesoscale models. These are models that use relatively fine meshes. The size of the elements in these models are on the order of microns, and they require constitutive properties of all the subzones. So the issue is that because we have a heterogeneity in terms of the peak temperature that is experienced in different regions of the spot welds. So for example, as we go from the fusion zone towards the base metal, we have different meteorological transformations that are occurring because of that gradient in terms of the peak temperature. Now, this means that we're going to have differences in terms of mechanical performance of all the different subregions as shown on the right-hand side here as well. So adoption of these type of models, the mesoscopic models, are really going to be informative in terms of the mechanics of fractures. So things such as the crack initiation region, crack propagation path, they're going to be modeled very accurately in such models. But on the downside, since these models are using really small element sizes, they're going to be very computationally demanding, and it requires a lot of fracture characterization for different subzones, which can be challenging. Now, sometimes the goal is not to have all these minute details in the fracture. The goal is to, for example, model the behavior of a component comprising of multiple spot welds as shown at the bottom left here. Now, there is actually a second group of studies that use force-based models. Like these models use relatively coarser meshes relative to the mesoscopic models, and they model the whole spot welds and its surrounding heat-affected zone with limited number of elements, as shown on over here. Now, the main input in such models is a failure loci that determines the onset of failure for different loading modes. I've shown an example of such failure loci on the bottom right here for shear versus tensile loads, and you can see the failure loci is determined based on this curved shape here. Now, the accuracy of the force-based models ultimately depends a lot on how accurate our failure loci is, which is one of the main topics and motivations of my work. So I'm going to get into a bit more detail on that. Now, the most common failure loci equation, the functional form of the failure loci equation, is proposed by Seeger that is adopted in LS-DYNA's MAT 100DA material card. Now, as I've shown here, this failure loci uses two terms. The first term deals with shear strength. The shear strength of spot welds is typically characterized by performing lap shear test, which is a standard test. And we can put the shear strength of the weld on a plot like this, where the x-axis is shear load and the y-axis is a tensile load. The second term of this equation proposed by Seeger deals with tensile strength that is characterized by cross-tension test, and we get the tensile strength. Now, in the most basic form of this failure loci, we can fit a curve through these two data points and get our failure loci. But the issue is that we do not really have any data points at the intermediate loading conditions, and that's why the KS2 tests here come in our help, where we can perform mechanical tests at intermediate loading conditions in different ratios of shear tensile load components, other than the two extremes performed by lap shear or characterized by lap shear and cross-tension tests. Now, what ended up happening a few years after Seeger suggested this equation, they actually added a third term to their initially proposed equation, where they essentially transformed their 2D failure contour into a 3D failure surface. This third term deals mainly with bending strength of the spot welds that is commonly characterized by the Coach-Peel test. The Coach-Peel test, I've shown a schematic of it here, where there is an offset between the loading axis and the location of the spot weld. Now, in terms of the combined shear tensile loading of the spot welds, we typically have a customized fixture that is able to accommodate different proportions of shear and tensile loads. And what we get from these tests is going to be load displacement curves at different loading ratios. And these load components can be decomposed into their comprising components in terms of shear strength and tensile strength. And we can fit a curve through them to get our most accurate failure loci. Now, the issue is that the mechanical tests, they don't follow the initial ratio between the shear and tensile load that we intended for the whole duration of the test. I've shown an example of it here where the test is initiated at 45 degrees, and the authors actually acknowledge that we have rotation or slippage, some sort of rotation and slippage throughout the test that is changing the ratios of the load applied to the spot weld. This is also an issue with other mechanical tests, such as the standard lap shear test as well. So the deficiencies that really exist in terms of characterizing the behavior of spot welds in shear tensile loading is we are not really quantifying the slippage or rotation of the coupons, and we're having inaccurate critical shear and tensile load bearing capacities at the onset of failure for the spot welds. Now, the situation for tensile bending loading condition is actually much more complex because we don't really see an effort in the literature in assessment of whether or not the convex assumption of the failure loci suggested by Seeger is accurate. This is really because we have a severe amount of deformation in coach field tests, and it's very difficult to comment on the evolution of the bending moment. So as I've shown on the left-hand side here, this schematic really assumes that the upper arm of the coach field coupon remains perpendicular to the lower coupon throughout the test, and that the spot weld maintains its alignment from the beginning of the test to the end of the test. But when we compare such tests, such schematics with the actual footage or images of the coach field test, we see that they don't really go together, where we have severe amount of deformation and the rotation of the joints throughout the test. So another issue with the coach field test is really that we are not able to comment on how the bending moment is evolving throughout the whole test. The bending moment is going to be the instantaneous load applied to the spot weld multiplied by the instantaneous moment arm. But this moment arm is going to be continuously changing from the beginning of the test to the end of the test, which is not commonly tracked in the available literature. Now, in terms of the component tests, there are a few purposes that we would perform component tests. So we would either characterize sequential failure or a progression of the failure between adjacent welds, or we want to validate our models that have been calibrated using single spot weld characterization techniques, such as the lap shear, cross tension, coach field, or the KS2 test. In the component test that we performed is referred to as the Cayman test that was basically suggested at the University of Waterloo. You can see the geometry of this component. It is comprised of two hat channel rails that are welded together on the flanges. And from what we know from the literature is that the mechanical performance of the spot welds that we attained from the Cayman test really depends on ductility of the flanges where the spot welds are located. So in a study in 2021, what we really understood is that if we tailor the properties of the flange by heat treating it, we can improve the mechanical performance of the weld by increasing the ductility of the flanges. But it is not really clear how the manner in which spot welds fail affects the mechanical performance of such component tests. We know that spot welds can fail in different manners. For example, we can have interfacial failure, where we have propagation of the fractures through the sheet interface, or we can have pull-out failure, where we have propagation of the failure away from the sheet interface through thickness direction, or a combination of both in partial interfacial, partial pull-out failure modes. Now, based on that introduction, I have a few motivations in my presentation today. First off, I'll optimize the process by developing weldability lobes and attaining welds that have the highest amount of load-bearing capacity and energy absorption capability in standardized lap shear and cross-tension tests. Then I'll look at the mechanical performance of spot welds under shear tensile and tensile bending loading conditions. There's going to be an emphasis on the neglected aspects of these two types of loading conditions, which is specifically the accounting for the rotation or any slippage or the evolution of loads and moments that are happening throughout the test. And lastly, I'll take a look at the mechanical performance of a group of joints under tensile bending loading conditions by performing the Cayman mechanical test. So starting off with the first chapter of the results, for the materials that have been used in my study, we're using two grades of third generation advanced high strength steels. I'm going to be referring to them as 3G 980 and 3G 1180, where the 980 and 1180 corresponds to the ultimate tensile strength of these two steels. You can see representative scanning electron microscope micrographs of these two steels, where we have different phases present at the microstructure, specifically the retained austenite, which I mentioned is the one responsible for the trip effect. And we have different, basically, volume fraction of hard and soft phases, which is characterizing the difference in the strength of these two steels. At the bottom, you can also see the chemical composition of these materials. And on the right-hand side, you can see representative standard tensile tests performed on the as-received parent metals. In terms of the RSW process, we're using a double pulse welding schedule that was suggested by the American Welding Society standard. That's the most commonly adopted standard in the North America for spot welding. Now, we actually changed the welding current from a really low amount, around 6.5 kiloamp, up to 10 kiloamp to attain different nugget sizes. Our squeeze time was 10 cycles. The length of the pulse is also 10 cycles, with 2 cycles in between the two pulses and with a 10 cycle hold time. You can see the weldability current range for the two steels at the bottom here, which basically divides the domain into 3 regions where we have unacceptable welds because they're too small, acceptable welds, and the welds that are formed via expulsion. So once we looked at these, once we developed this weldability lobe, we performed a standard lap shear and cross tension test. At the top, I'm summarizing the peak load of the lap shear and the cross tension test at different welding currents. At the bottom, I'm showing the amount of energy that was absorbed, which is the area underneath the load displacement curve for these two tests, the lap shear and the cross tension test. And the highlighted welding current is actually going to be the optimized condition with the highest amount of load bearing capacity and energy absorption capability. And the welding current selected is also written on the right hand side, which was 9.1 and 9 kiloamps for 3G 980 and 3G 1180 respectively. Now you can see all the optimized electrode face diameter weld size, the cross-sectional view of both steels. We're having a nugget diameter of 7 millimeter for both cases. So any changes or differences that we see in terms of mechanical performance is not going to be really related to differences in nugget size. We performed lap shear, cross tension, and coach field tests. You see the representative load displacement curves for these tests. And from these, we extracted the peak load and constructed the 3D failure contour surface that was suggested by Seeger. Now, note that in the equation of these failure contours, the exponents are all equal to 2. That's traditionally accepted because we don't really have the data points to optimize these exponent values. So let's start off by looking at whether or not how accurate the failure surface is in the shear tensile loading domain, which is the dashed red line at the bottom of these failure surfaces. For that, as I mentioned in the beginning, we performed the KS2 test at intermediate loading conditions or various shear and tensile loading ratios. You can see the methodology for the KS2 test in this slide. It is comprised of a U-shaped coupon with the dimensions shown here. We joined 2 of these U-shaped coupons together with the spot weld at the mating interface between the 2 coupons, and the coupon itself is mounted on a holder with different components, and this holder is able to rotate and accommodate different ratios of shear and tensile loads being applied to the spot weld in 5-degree increments, as shown on the right-hand side. We performed our test starting from 0-degree loading orientation all the way up to 90, adding to the tensile component of force that is being applied to the spot weld. We performed our tests in 8 different loading orientation. We also performed it at 10 degrees, which is not shown in this schematic for clarity. You can see the assembled CAD design of the whole fixture. And we also coupled all of the KS2 tests with digital image correlation so that we're able to track any rotation or slippage or deformation that is happening throughout the mechanical tests. Let's take a look at a few videos for different loading orientations of the KS2 test. On the left, I'm showing a KS2 test at 0-degree loading orientation, representative of the pure shear. And on the right, I'm showing it at 45-degree loading orientation, so ideally equal proportions of shear and tensile load being applied to the spot weld. Now, the issue is that as the tests continue, we have a non-negligible amount of rotation that is happening in shear-dominated loading orientation, but that's not really an issue in tensile-dominated loading orientation, as shown on the bottom right-hand side here, where we are essentially maintaining our alignment throughout the whole test. So this is not really an issue in tensile-dominated loading orientations, but it has to be accounted when we're constructing our failure loci for shear and shear dominated loading orientations. Now, in order to do that, we developed this methodology that is we're referring to as the triangulation method. What this method essentially does is that it tracks the instantaneous orientation of the nugget from the beginning of the test to the end of the test. And the way that it does that is we're using circular inspectors from the DIC and post-analysis and we're constructing two triangles on each, one triangle on each KS2 coupon half. And by approximating the projected this nugget center point from each coupon half, we are able to track the displacement that we have from each coupon half throughout the whole test. And this way, we're able to track the displacement of the weld in shear direction or tensile direction, and we can at the same time track its orientation throughout the test, as I've shown in the videos on the right-hand side that are synced with the experimental footage. So but the output of this test is going to be the peak loads, as I've summarized here for both of the material. The 3G980 is the one in red, and the 3G1180 is in blue for all different loading orientations that we performed. And we also have the amount of rotation that we have at the onset of failure until the onset of failure, as I've shown summarized in the graph at the bottom here. Now, what we can do from this data is that we can decompose the peak load into its constituents, which are shear load and tensile load nominally, which is done at the top here. So that means, for example, if a test is performed at 15 degrees loading orientations, we're going to assume that the weld is going to maintain its alignment from the very beginning to the end of the test. But if we actually account for the actual orientation of the weld from the beginning to the end, we can see that the evolution does not follow a linear trend, and it actually curves upwards, where we get a more contribution from the tensile component of force being applied to the spot welds. Now, by having these data points, we can reconstruct the failure loci in the shear tensile loading conditions as compared to what we had initially. So initially, we just have lap shear and cross tension data points. Those would be the two black dots here. But we can add the nominal loading ratio that we got from the KS2 test in all the intermediate loading orientations. This is still the nominal one, which is following the nominal dashed loading orientation, but we can update it by the actual final ratio of the shear load and the tensile load being applied to the spot weld, so we can see how that initial failure loci is expanding and giving us a more accurate representative failure loci that can be implemented in our models. Now we can update our 3D failure surface after performing the KS2 test. So you can see at the bottom plane here, we have more data points, and we actually have the optimized value of these exponents for the first two terms at least. Now, still the issue is that we are not able to optimize this third value, the exponent value, which is dealing with tensile bending loading condition, which brings us to the third chapter of my study, which is dealing with tensile bending loading condition of spot welds characterized by the coach field test. Now, in order to add data points on the tensile bending loading domain, we actually have to perform our coach field mechanical tests in different geometries to change the ratio of tensile load and the bending moment that is being applied to the spot weld until the onset of failure. This is the methodology of the test. You can see the coupon geometry. The coupon geometry is the same for all the geometries that we use except the length of the flange. You can see a schematic of two of these L-shaped coupons being joined together with the location of the spot weld being here. And you can see that there's an offset between the axis of loading and the location of the spot weld. We obviously coupled all of our tests with DIC again to track the evolution of all the forces and moments applied to the spot weld. I'm going to be referring to the coach field test with the three geometries of short arm geometry, where we have a horizontal arm of 19.5 millimeter. We have a medium arm length geometry with an initial arm of 25 millimeter and a long arm geometry with an initial arm of 32 millimeters. Here I'm showing an example of the deformation that is happening throughout a coach field test. And this is really highlighting what I was showing in the introduction, where we have discrepancies between the schematics that are being drawn with respect to how coach field test is really progressing from the beginning to the end of the test. I've shown three snapshots from the beginning of the test on the left, the peak load frame of the test in the middle, and the final fracture frame at the right-hand side. And you can see how the initial arm, which is this D term here, is actually essentially reducing throughout the whole test. And we're evolving these angles as I'm referring to as 2 alpha and beta and lambda here, or gamma. So the evolution of all these moments and the moment and the loads can be tracked if we perform an equilibrium analysis on the coach field specimen. And now to do that, since our tests are all performed in quasi-static strain rates, we should have equilibrium holding throughout the whole test. And that's why we performed a static force equilibrium analysis on the coach field coupons. So we're using inspectors located on 4 inspectors on each coupon, L-shaped coupon P1 to P4 and P5 to P8. And this way, we're able to track all the deformations that are happening throughout. We can have the evolution of the bending moment arm. We can have the evolution of these angles. And as a result, we can get the force components and the bending moment that is being applied to the spot weld, the actual value of it throughout the test. So if you look at the equations at the bottom for shear force, tensile force, and the bending moment applied to the spot weld, you can see that they're all a function of geometry, which is these trigonometry functions at the bottom here. Now let's take a look at the evolution of some of these parameters in an example of the coach field test. So this is an example of the short arm geometry, where the black line here is the traditional load displacement curve. But at the same time, you can see that the red line is showing how the effective bending arm applied to the spot weld is changing. So initially we had around 10 millimeters of unbending arm, and that number is reducing to less than 3 millimeters by the end of the test. And at the same time, we have an increase in the orientation of the nugget. What is interesting is that as we cross the peak load frame, the rate at which the arm reduces and the nugget orients itself more is changing, because the sheet is actually detaching from one side and it's rotating at a faster pace. We can also plot the force components and the moments at the same time. The black shows the bending moment, the red shows the tensile force component, and we also have a negligible amount of shear force developing throughout this test. This test is really not intended to develop shear force, so the magnitude of the shear force is really low. We can extract the critical values of the bending moment and the tensile and shear load components and use them for calibrating our failure loci in tensile bending loading conditions. So let's take a look at the summary of these critical load and moment values at the onset of failure for different geometries of the coach field test that we performed. And the red shows the peak load of the test. As we go from the short arm to long arm, we have a decreasing trend. Same thing with the tensile component of force, but we're getting a higher and higher contribution of the shear moment, shear force component, but which is still quite negligible. It's less than 1 kilonewton in all cases. And at the same time, as we're reducing the effective tensile load component applied to the spot weld, as we go from the short arm geometry to the long arm geometry, we're getting a higher and higher amount of bending moment that is being applied to the spot weld at the onset of failure, which is shown with the blue bars here in these two graphs. So now, if we add all that data point in the failure loci that we had initially, we can really tell that the initial convex shake that was postulated by Seeger in terms of the behavior of the spot walls in tensile bending loading conditions does not really hold. So on the right-hand side, you can see the data points for the three different geometries of the coach wheel. The black is the short arm, the red is the medium arm length, and the blue is the long arm. You can see that the trend that we're getting is more of a concave shape that better basically predicts the behavior of the spot wells in terms of their tensile bending loading condition. Now, coming to the last chapter of my result, where we deal with the component test under tensile bending loading conditions characterized by the Cayman test. So that you can see the methodology of this test in this slide here, where we're using two hat channels, hat section channel rails. We coupled all of the tests with optical cameras and thermal cameras to track the onset of failure for different spot wells that are located along the flange. You can see the fixture that we use to perform these tests on our tensile frame. I've summarized the load displacement response of the two tests. What we essentially see is a discrepancy in terms of the peak load and the energy absorption capability. Specifically, the 3G 980 is showing us superior performance. And what we really want to know is why this is happening. What are the major factors that are influencing the energy absorption capability between these two materials? And once we look at the data from the optical camera and also the thermal camera, we can see that sequential failures happening on both sides, but by the end of the test, we have a more severe collapse of the sidewalls in terms of the 3G 980 material. And this sidewall channel collapse is definitely contributing in terms of the energy absorption capability between the two materials. So one of the reasons that we have superior mechanical performance from the 3G 980 is definitely going to be this more ductile flange that we have in the Cayman component test. But at the same time, when we look at the rate of failure that's happening throughout the different crossheads, so we are using this index that we're referring to as the opening length, which is the length from the fixture to the first intact weld. And we're always seeing that the failure is initiating sooner for 3G 1180 material at a lower crosshead displacement relative to that of the 3G 980 material. And to investigate that more, we looked at the failure behaviors that we're seeing in these tests, specifically for the 3G 980 and 3G 1180. I've shown representative micrographs here. And these are the the last four wells that are failing by the end of the Cayman test at 250 millimeters of displacement. And you can see that we're continuously getting a complete pull-out failure from the 3G 980 material, characterized by failure starting from outside of the nugget and then propagating around the periphery of the nugget, giving us a relatively high plug ratio. Whereas in the case of the 3G 1180, we're typically getting partial interfacial, partial pullout, where we have crack propagation inside the fusion zone and giving us a relatively smaller plug ratio by the end of the test. Specifically in terms of the fractography of the test, we're getting more ductile failure, represented by the dimple features of the fractography for 3G 980, whereas we have more of a mixed failure with predominantly cleavage facets, representative brittle failure for 3G 1180. So definitely this is another reason we're getting differences in terms of mechanical performance. Now, we also performed, in order to understand how the failure behavior is actually affecting our mechanical performance, we also performed a modified version of the coach field test that allows us to see in situ the evolution of the strain that is happening or the failure that is happening throughout the test. We sectioned the wells in half to observe and allow for a window for DIC observation. And what I want to highlight is that in the case of the 3G 980, consecutive failure under tensile bending loading conditions is resulting to around 10% strength loss from the first weld that is failing to the second weld that is failing. But when we get our partial interfacial, partial pullout failure in the case of the 3G 1180, we're getting a much more catastrophic strength loss in between the adjacent spot weld failures. So what that really means is that if we get brittle partial interfacial partial pullout failure, which is the case for 3G1180, that definitely is affecting our load displacement response. And that is another reason that we have inferior mechanical performance in the case of the 3G1180. So essentially, we have two parameters that are affecting the mechanical performance of sequential weld failure. The first one being the flange ductility, and the second one being the weld failure behavior. In terms of the modeling response, we calibrated our models from the experimental data points from the force displacement, and that was the target for our simulations. We developed LS-DYNA simulation models for each of the single spot weld characterization techniques. So we're not showing all of them, but these are representative developed models for the KS2, lap shear, and coach build test. And the boundary conditions were all extracted from the KS2, the test in terms of the KS2 simulations. And we compared the load displacement response between different single spot weld characterization tests. I'm showing the results for lap shear, KS2 at 45, and the coach build test for 3G980 at the top here for three different LS-DYNA models. Specifically, the blue lines are the experimental data points. The red is the calibrated LS-DYNA model from the MAT100DA. The black one is the MAT100, and the blue is the 240 simulation. Now, in terms of the calibrated Cayman models, you can see the results here, again, for the same three models. The weld failure surface from the single spot weld characterization test, where you calibrated, the model was calibrated using the single spot weld characterization test, and it was its accuracy was analyzed in the component test. And you can see the comparison here, where we have relatively good agreement in terms of the peak load, but the energy absorption capability is being under-predicted. So with that, I come to the conclusion aspect, the conclusion part of my presentation. In my study, we really accounted for the evolution of the load components and the moments that are being applied to this spot weld until the onset of the joint failure during KS2 test and the coach build test. We also assessed whether or not or how valid the conventionally accepted force-based failure criteria suggested by Seeger is under different loading conditions. So Seeger's criteria can be used for shear tension loading conditions quite accurately, where we had an over prediction of around 3.5% at most. But Seeger's criteria cannot be extended to bending dominated loading conditions, where we had a huge amount of over prediction in terms of the bending strength up to 66%. In our study, we also developed novel DIC-based methodologies that can be used to account for the evolution of the geometry throughout different mechanical tests and give us the instantaneous values of forces and moments that are being applied to the spot welds. We actually also determined that two factors dominate the energy absorption capability of spot welds, like group of spot welds failing under tensile bending loading conditions of the Cayman tests. We have the contribution from the plastic work due to parent metal ductility, and we also have the failure behavior that is contributing in our spot weld failure and mechanical performance. We also developed single spot weld mechanical properties that were used to build industry standard LS-DYNA material cards that predict the spot weld failure under combinations of load scenarios. And with that, I come to the end of my presentation. I will be glad to take your questions now.
Thank you. Thank you very much, Mohammed. This was really interesting. I bet this research is guaranteed to have a lot of great value for both the steel industry and the automotive industry alike. Second, let me remind the participants, if you wish to submit a question, please submit it through the Q&A feature. With that, let me go to the Q&A feature. I have a few things here. Most importantly, I think Dr. Karagoulis has given you kudos for a very nice work and presentation. He also commented on the fact that the Achilles heel of the advanced high-strength steel spot welding is that the weld strength does not keep pace with the base material strength. And you have captured the metallurgical problem very well. Because carbon seems to be the enemy of weld strength. So he's asking, do you have any comments on this?
So the thing that we focused a lot is this neglected aspect in the literature, which was really this not accounting for geometry throughout the mechanical tests. So in terms of, yeah, I know, like as we go up in terms of the strength of the steel, the joint is not really the critical factor. But once we account for the effect of geometry in our mechanical tests, we can definitely improve our prediction accuracy, especially in the case of the force-based models.
Okay, let me move on to another question. Have you considered single weld with 3 or 4 sheet stack-ups? Or is that still too early?
We have some projects that we're working on multi-stack-up geometries. It gets a lot more complicated in those cases because especially in the case of having this similar stack-ups with different strengths and different thicknesses of the sheets, you get this issue of the penetration of the fusion zone in different sheets is not equal. So you really have to manipulate the welding schedule quite a bit to get a good nugget in multi-stack-up geometries. So that's a huge challenge that we're working on in our lab. But these results that I've shown today, they're all related to 2 stack-up similar sheets. So 3G 980 with 980, 3G 1180 with 1180. But they can definitely be extended to multi-stack-up or the similar geometries as well with the same concept.
Great. Another one that asks, was this approach validated in an actual car crash model or reduced crash model in order to see how this failure works in actual crash events?
Yeah, so I guess that would be the ultimate goal, right? So we would want to see more accurate representation of the actual crash scenario. The tests that our study is more of a fundamental study where we're proposing this methodology at least highlighting the fact that geometry matters a lot. It's not just the way in which the spot weld failed that determines the mechanical performance. We have to account for the evolution of all these force components and the moments that are being applied to the spot weld according to the geometry. Our tests are not perfect, like the coupons deform, especially, for example, in the case of, like I can show here, we have cross-tension test being a standard test, right, on the right-hand side. And you can see that in the case of a softer steel, so let's say 980, I'm not saying 980 is a soft steel, but relatively lower strengths, we get a lot of deformation on the base metal. And that base metal deformation is contributing to the energy absorption capability that we're contributing to the spot weld. So that's not necessarily the case. So these 2 concepts are intertwined, and we can kind of distinguish them by performing tests such as KS2 test, which brings a much better defined boundary condition and is able to basically distinguish those properties in terms of the spot weld and separate it from that of the base metal.
Okay, well, that actually let me hold off to my question here, but you got another question related to maybe, have you ever done any of that stuff on PHS 1500 or 2000?
Yeah.
Material? Okay.
Yes.
Can you touch on what the challenges and difficulties are during the testing?
The situation is much better for higher strength materials because the material is so stiff and you don't really get a lot of the coupon deformation, at least in those materials. So with PHS 1500 or UC bore or ductile bore, either of them, the rotations that we're getting from our DIC analysis is much less severe compared to, for example, the 3rd Gen 980 or 3rd Gen 1180 that are relatively softer. So the idealized shape of the failure loci in shear tensile loading is much closer to the one that we have from after accounting for all the orientations in those cases. But the situation gets much worse in softer steels, such as the 3G 980. We have all the data for the PHS as well. We have published part of it, but this was not included in this presentation, the data for PHS.
Okay, well, it's good to know. Shriram asks, this is a very interesting presentation. What does the micro-hardness profile for the 2 materials look like? Do you have any comments on that?
think I've shown it. Yeah, so the microhardness profiles are here. In the case of the 3G980, what is interesting to mention is that in the subcritical regions around here, we have some secondary hardening. But in the case of the 3G1180, we have softening in the subcritical Has region. The fusion zone of the 980 is slightly harder than that of the 1180. That's, I'm guessing, mainly because of the higher carbon content of the steel, which is increasing the hardenability of it. We also have a paper that's directly analyzing these and like addressing all the different phenomena that are happening in different regions. Especially, what was really interesting to us was the secondary hardening in the 980 and the softening in the 1180. And we've done extensive TM analysis on that in our lab. And what we saw is that we have carbide particles that are forming that are responsible for those hardening that we're seeing in the subcritical Has region.
Okay. There's another question regarding the heat affected zone. How did you address the heat affected zone, if any?
So the model that we're developing is not a mesoscopic model. We're calibrating our failure loci by looking at and processing our mechanical tests more accurately. I'm not really characterizing the heat affected zone mechanical performance, although we have done that in our lab. We have actually recreated a representative microstructure by using Glebo thermomechanical simulation and pulled them apart to get the representative stress strain curve of the heat affected zone. That was not included in my presentation because what I'm focused on is really creating a more accurate version of force-based failure loci that is used for force-based models.
Okay, good. And I think we're kind of running out of questions. I think one final comment here from Mike Karagoulis indicating that it would be interesting if you also do these types of studies with weld-through adhesives in the joint. Maybe that would be your next GDIS presentation, Mohammad, right?
I haven't worked on adhesives, but that would definitely be an interesting topic for sure. Yeah.
Yeah. So with that, I think let me just touch on one last question before we hop off. If you do not consider the bending angle change on your weld failure model, how much do you expect the accuracy of the LS-DYNA crash simulation as compared to actual crash tests? I think this is kind of like subjective.
Yeah, again, so that would be the ultimate goal, where we have these modified failure loci that should be implemented in the material card of the LS-DYNA. I haven't performed the test in terms of the crash performance of the components to see how much the traditional failure loci differs in terms of the prediction accuracy to the modified ones, but that would be definitely a future work for us. Okay.
Very good. So there are other questions related to the availability of the video of the presentation. As Brian had indicated, this will be available for view. The PDF and the video will be available to the participants. So with that, I'm going to let Brian jump in, conclude this webinar.
Mohammad Shojaee, thank you so much for the presentation, the Q&A discussion, and thanks to everyone for joining us today. Just as a reminder, Mohammad's presentation, as well as this recording of this webinar, will be posted to our website. We'll make it available on the steel.org, autosteel.org, and Great Designs in Steel websites. You'll be able to access those there. Watch for news about our upcoming Great Designs in Steel technical webinars starting again in first quarter. And mark your calendars for Great Designs in Steel, May 21st, 2025. Our registration, we will open in January. And in the meantime, our call for speakers is still open. If you've not submitted yet and you'd like to make a presentation, please submit your abstract at the Great Designs in Steel website as soon as possible. Thank you for joining. Have a great day.